Hello and welcome to the final lesson in rotation. This is AP Physics 1, elliptical orbits. This is kind of a special case application of angular momentum, pretty specialized. So that's why I kind of gave it its own special video here and why it has its own special section here in the notes. I added a little bit more material to the Canvas page, and there's a couple of formulas, one in particular that I haven't addressed yet that's in these notes that I usually do earlier, and I'm going to show you that as well as we get into this. In fact, before I forget, let me go ahead and show you this. Um, v equals, V is linear velocity equals omega, which remember is angular velocity times radius. That's a pretty important formula that's kind of glossed over at times, but it's really helpful in determining some situations, like if you want to know linear velocity and you know these two. And this is kind of the basic derivation of it. If you go from back to circular motion, v is equal to 2 pi r over t, and you do a little substitution there, where if you're in a complete circle, angular velocity is equal to angular displacement over time. Well, your angular displacement is 2 pi radians, and then your t is your period. And so that kind of is a derivation there. And that also leads to another one that's a little, less, but it's good to know anyway. Linear distance is equal to angular displacement times radius. So you see the common factor there is multiplying the radial distance times the rotational analog will give you the linear analog. So pretty useful there. I'm going to show you that once we get into the slides here as well. Okay, so elliptical orbits. A little bit new terminology in this one as well. So you see, here's the sun, and we basically have a body in an elliptical orbit going around the sun. So this is just, a generic planet, whichever. And we have the major axis, which is defined as 2a. A is kind of not necessarily half that, but generally determined as the average distance between the two objects. Like if you have an object here and then here, you have this in R1 and R2. A is kind of the average between those two. And we're going to look at this in terms of both conservation of angular momentum and conservation of energy. We're going to bring those into this as well. So looking at this in terms of conservation laws, we can see here that at this point where the planet is closer to the sun, it's going to have a greater kinetic energy and a lower potential energy. Think of this as a ball dropping. This is when it's getting a little bit nearer to the floor, where most of its potential energy has converted to kinetic. So the closer it is to the gravitational bodies going around, the more kinetic energy is going. In other words, the faster it's going. And then the farther out you go, the opposite is true. The more potential energy it has. And this is what's referred to as kind of a gravitational slingshot, actually. And just for your information, this is actually how Apollo 13, NASA was able to use this gravitational slingshot. Apollo 13 was the NASA craft that was damaged, and it was going to land on the moon, but once it was damaged, that was thrown out the window, so they needed to get the astronauts back home. So they programmed it to do kind of a gravitational slingshot around the moon, and that helped to save a bunch of energy that helped them to get that back home. So nice little application there. But as far as angular momentum here, taking the central body to be the axis of the revolution, there's zero torque due to gravity. Okay, why is there zero torque? Well, remember our definition of torque, RF sine theta. Well, and remember when theta, the angle of the force is pointing directly back on the lever, there was zero torque. So wherever this is happening, that's going to be the case because that gravitational force is towards the sun there. So because of that, the angular momentum is going to remain constant there. And also, as long as we don't have like another planet that's out here or space junk, nothing else that's influencing the orbit aside from the gravity of the sun, the total mechanical energy of the system is also going to remain constant. So think of those principles that we learned back in both momentum and energy there. So a little bit new formula derivation being thrown out here. Angular momentum, remember, is L times I omega, I being rotational inertia, omega being angular velocity again. If we do a little bit of substitution here, I being mr squared, which is rotational inertia of a point mass, and planets in this case we're considering more or less a point mass. And this is that formula that I showed you the derivation for. I didn't want to just throw it out for you without explanation. Now this one was included in the first Boson video I linked to you, but you may have missed it. So in this case, omega is V over R, or V is equal to R times omega. With that, we get a new formula here. L equals RMV. In other words, your angular momentum can be defined as your radial distance times your mass times your linear speed. One qualification here. This really is only valid when the radial distance is perpendicular to the velocity, the tangential velocity, because we're talking linear velocity, not angular. Because anywhere else, if you imagine we're looking at here, we would have an R like this, but we have a V like that, and that would really complicate things. So we have to have that qualifier that we're only talking about at basically 2 points, either the shortest possible distance away or the longest possible distance. So when we're looking at this conservation momentum, we have to have it being one of those two things. So we can set this up, since this is conservation, we know that L is equal to L prime. In other words, the angular momentum at this spot is equal to the angular momentum at this spot. In other words, there's a, you increase the radius, you decrease the velocity, and vice versa. And that leads us into this last page here. I think this is, yeah, that's the last page. A whole lot more new stuff here. This is looking at this in terms of conservation of energy. Now, first of all, you might notice, okay, wait a minute, we kind of threw out that whole perpendicular thing. Well, remember, energy is not a vector. Momentum is a vector. Energy is not a vector quantity. So we don't have to worry about where we're taking that. We just know as long as there's no external forces here, the conservation of energy is going to remain the same. We just need to know a few certain things. And we have this formula. This one is included on your AP formula sheet. U, which is potential energy at whatever point, is equal to negative big G, which is your universal gravitational constant, times the product of the two masses divided by the radial distance. And so if we wanted to know the total energy of the system, we would, just like before, we would get the sum of the potential energy and the kinetic energy at the times. Backtracking, we could also use this formula for the total energy of the system. Now, this is actually not included on your formula sheet unless I just totally overlooked it. So I don't think this is something you would have to be responsible for. AP doesn't make you have to memorize formulas, but I'm going to walk you through an application of this anyway. But you can kind of see how this would all plan out here. I wanted to save enough time to go over this one with this one problem, because it literally takes the whole page. But a lot of it is just a lot of it is just big numbers being set in there. Okay, so this is 26 on your classwork problems. Mars, and we get the mass of Mars, has an elliptical orbit in which its distance from the sun varies from 207 gigameters, and gigameters is 10 to the 9th, so that's 207 and 9 zeros, to 249 gigameters. Given that its minimum speed is 22 kilometers per second, and where is that minimum speed going to happen? Is it going to happen at the closest approach or that farthest approach? Yes, it is the farthest approach, because when you maximize R, you minimize speed. Determine its angular momentum at its maximum speed and find its change in kinetic energy and compare to the change in gravitational potential energy. All right, so let's get this in here, and I can probably, yeah, it's always good to have that right there. Okay, so on my sheet, I kind of put those formulas up there just for my own reference. And I also had to bring in the mass of the sun here, and this can be taken from your data table sheet that we used in periodic motion. Hopefully you still have that around. If you don't, that's on Canvas. And did a little diagram here, very similar to what was shown in the slides, where this is R1, this is R2, and this is Mars going around the sun. And big M is the mass of the sun, little m is the mass of Mars here. I want to first address the right here, determine its angular momentum and its maximum speed, because actually those are one and the same. We could do both of those in the same calculations. I can set this up as we saw in the slides of, L equals R and V, and L equals L prime. So this is L prime, and just put in values. Now, I want to be very careful here. I've got 207 gigameters just so I can fit it on the page, but that is actually going to need to be in your calculator 207 and 9 zeros, because we need that in meters for this to work. So that's 207 gigameters times the mass of Mars times V1, which is the speed we're trying to solve for right here. We're trying to solve for its maximum speed, because we're given minimum speed, equals 249 gigameters times the mass of Mars times the 22,000 we were given. Again, 22 kilometers per second needs to be in meters per second. So once we do the algebra for there, we get 26,463.8, which we're going to round off to 26.5 kilometers per second. So that is the maximum and minimum speed of Mars by these calculations. Minimum speed 22 kilometers per second, maximum 26.5 by these measurements. And then if we want to find the momentum, angular momentum, we could just solve either side. I could solve this one, which I already had, 249 gigameters times the mass times the speed, or the other one that I have that. And either one is going to give me 3.52 times 10 to the 39th kilograms meters squared per second. Now, if I go on down here, I'm going to be looking at this in terms of change in kinetic energy and compare to the change in gravitational potential energy. Like I said, that this formula does not appear on the AP formula sheet, like I said, unless I just overlooked it. This one does, but I'm going to walk you through this anyway. So we know that, again, U1 plus K1 equals U2 plus K2, because we don't have any non-conservative work. It's all gravity. Another useful thing here, R1 plus R2 is going to give us this 2A here. So whatever those two measurements are, that's going to give us that major axis that we need to solve for the total energy in the system. And gravitational constant, 6.67 times 10 to the negative 11th. Kinetic energy is going to be equal to the total energy minus the potential energy. Nothing new there. So we just start to do some formulas here. So this is formula for E, this is formula for potential energy. We start to put in some really large numbers. I have to scoot this up a little bit so I can show it all. Gravitational constant, mass of the sun, mass of Mars, plus the sum of the two radial distances. And again, I've simplified this, but this should be in meters, not gigameters when you do your math, minus the value for potential energy there. And then once you kind of get all of this in, and you notice that this and this are the same, so that kind of helps you out there. But eventually you're going to get this value right here, 2.25. Remember, this is the kinetic energy at the closest point. And then I do the same thing again for the, at the farthest point. Notice that instead of 207, I use 249. The first part's the same because total energy doesn't change. And then at this point, my kinetic energy has dropped to 1.55 times 10 to the 32 joules. Still a massive amount of kinetic energy. So the change in my kinetic energy there ends up being 7 times 10 to the 31st joules. Now, if I go back and do the same thing for the change in potential energy, I get the same value, which should make sense because conservation of energy tells us I lose kinetic energy, I gain potential, and then vice versa. I gain potential, I lose kinetic. All right, just wrap that up. So just let me know if you have any questions.